Hello. Sure. Hello, guys. A few words before we start. My name is Roman Stratienko. I'm embedded engineer from Global Logic. Last couple of years, I was working on boosting generic Android hardware abstraction layer development. And the ultimate goal of our team is to create Armbian-like distribution for Android, which require a few steps to bring up on any existing board. And at this moment, we are working on with a small amount of ARM-based devices, but let's say our ambition is to cover all available hardware. I'm seeing Android as yet one Linux user space and believe that with some adjustments, it can run on any hardware that mainline Linux can work at this moment. The thing is, Android core team isn't working in this direction. And major effort is done by Chromium OS team, Intel, Linaro, and other teams, but the effort are usually focused on particular commercial hardware. To fill these gaps, we've started GloDroid initiative and successfully working in this direction for quite a while. Now let's come closer towards topic of the talk. One of required component of Android hardware abstraction layer is Gralloc. These days, Gralloc means three APIs, allocator APIs, mapping API, and starting from Android 11, buffer metadata access API. Okay, today we will focus on allocator API since despite API is very simple, implementation is the most challenging in current platform software conditions. So API consists only from one call, allocate, with four required parameters, width, height, format, and usage flags. API works like that. The user requests allocator service to provide the buffer for using biographical hardware or software components, and HAL is responsible to allocate the memory using operation system ioctl and prepare the buffer metadata information. The most challenging logic, as it turned out, is the metadata information preparation and correct heap selection. Let's go next. Okay, I can speculate that major challenges is caused by the development process of modern SoCs, where components were designed and perfected by different companies, isolated from each other. Company A was working on GPU, while company B was working on display controller, and compatibility between the components was poorly elaborated. Yes. Okay, let's see how display drivers are allocating memory for the frame buffers. Different drivers are doing different operations, which can be summarized down to applying four constraints: width alignment, height alignment, size alignment, or it may be called also page alignment, and heap selection. And we need to select heap because some hardware doesn't have MMU. It requires physically contiguous memory to operate, while some has MMU and can work with virtual memory. And for some of x86 discrete GPU, display controller can scan out only from internal memory, so it's another heap. So that we need to select. So similar can be found in GPU user space drivers. This data was obtained from Mesa 3D source code and video for Linux kernel drivers, which is responsible for video codecs, cameras, ISP, and etc. And so you can see the same adjustments need to be applied to match the hardware requirements. So width, height alignment, size alignment, that heap selection. Okay, let's go next. Let's try to design generic allocator for at least ARM platforms. Things start when user tell us which hardware will use the buffer. First, we need to obtain supported formats layouts for the hardware. Find command supported formats layouts. So we need to go to driver A and query the formats layouts which driver A supports. We will go to the driver B if it will be use buffer and request the formats layouts. Okay, then we will we have to select that format layouts which supported by both drivers or more drivers, and we should select the best format layout to match user requested format. And we actually can do that. Linux does that already, and all necessary API are available for that, so we can do it. Second thing that we need to do, we need to apply corrections mentioned before. So alignment for width, height, size, and select proper heap ID. And after corrections applied, buffer should fit the requirements of all selected hardware it will be used by. The problem is there are no API available to obtain these corrections, and unfortunately, Linux API wasn't designed with this in mind. There are some steps to address these issues from Linux graphics community, but still no solution available. So if you are interested in, you can find the presentation regarding graphical constraints on YouTube by searching for XDC 2020 allocation constraints, and you will find them. Okay, let's move to the MiniGBM, because to create a generic Gralloc, it's much easier to use and extend something that is already exists rather than invent from the scratch, and MiniGBM is a perfect candidate for that. MiniGBM is a generic allocator that can work for both pure Android as well as for Chromium OS. At this moment, it's the only open source Gralloc available which can pass VTS and the CTS tests. So there are a few more Grallocs available open source, but they are old or not supported anymore by anyone. And some advertisement from my side. Recently, we have ported GBM Gralloc logic to the MiniGBM as a backend. At this moment, driver can be used for pure Android and with limited capabilities without Chromium OS support, but it can extend Chromium OS Gralloc to work with more platforms, which MiniGBM can't work at this moment. Yes, let's go next slide. Currently, MiniGBM has a lot of platform-specific logic which works on x86 systems. Well, where almost all graphics hardware located inside GPU. But for ARM world, such approach will be very inefficient, but vendors can combine the SoC using different hardware sets for every design, vendors can reuse some graphical IP cores while upgrading another. So we always can have different combinations of embedded hardware. Yes, so as you can see from the slide, MiniGBM has platform detection code. Then inside platform detection logic, it has platform revision detection code. Then it has hard-coded format modifiers list for every component. It has hard-coded constraints. And it uses driver-specific IO to allocate the buffer. So it completely device-specific. All backends in platforms are completely device-specific. What we can do to fix this is using current approach, we have to implement new driver for each SoC, or sometimes even for every device. So there are a lot of boards available on the market. There are hundreds of them. So we can't go this road because we don't have such resources. But if we can describe each part of the hardware independently from each other, we can achieve the same goal with much less effort. So, for example, we can describe GPU as a set of formats modifiers and set of constraints, and select between GPUs only, and do the same for camera, codecs, display hardware, and then create the code logic which will find the common things, apply these common things, and allocate the buffer which will fit on all of these hardware at the same time. Let's switch to the next slide. So in a perfect scenario, we should define only constraints table for every platform and revision. And as was mentioned before, query API for format modifiers set is already available for KMS, video for Linux, Vulkan, GBM APIs, probably GL APIs, I'm not sure. And after we implement this query logic, we can reduce our local database, hard-coded database, to consist only of constraints for each of the graphic component. And step 3 is pushing constraints API integration into the major graphics APIs, into the KMS API, into the video for Linux API, which already have something like constraints API, into GBM, into Vulkan, etc. So we can join this movement. And after that, we can replace local database with query logic completely. And yes, what's next? And during initial print-up of such approach, we actually could keep CPU access to use always linear buffer layout. And later on, we may optimize and mapper part by implementing format coders, decoders. So when user need to work with the buffer using software, we can actually decode the buffer. For example, if buffer is tiled or compressed or in a different format, and allow user to work with this buffer. And then when user is finished to work with this buffer, we can decompress this and send it back to the original buffer. So this logic is already implemented in Mesa 3D, and in some cases this particular step can optimize overall graphics performance. So it at this moment is a long-term goal. Okay. After some brief look on constraints API proposal by Linux graphics experts and analyzing how KMS and GPU align in the buffers, it turned out that some platforms aren't using fixed values for alignments. For example, some platforms are using floating alignments, and alignment value depends on the bytes per pixel value, and same for height alignment. So it can depend on bytes per pixel value of the buffer. And also there may be different tricks for different formats. So I'm not sure how constraints API can work with these devices, and I have a little different proposal to the graphics community. So since we only need the valid metadata, when actually user space don't need constraints, instead of querying constraints, we can ask actually drivers to adjust our metadata using its custom logic, which can be very complicated. So I would like a graphics expert from both Linux and Android worlds to look into this proposal and share their thoughts. And we can also use this API to obtain the heap mask, heap IDs and heap mask, which particular driver can work on. And so the overall idea is to start from the no alignment and from any heap mask, and ask each driver to apply its constraints on top, to modify width, height alignment, size alignment, and to actually modify heap mask, which drivers can work with. For example, some drivers can work with CMA and system heap at the same time, but since system heap is more preferable, driver should also be able should suggest the user so to allocate the buffer and system heap. And after we transfer this validation structure between all the drivers, we can end up with correct metadata, correct aligned metadata, and with correct heap ID, which can be used later to allocate the buffer. So this is actually my proposal to solve this problem. And I believe that's all from my side. Is there any questions? I see not many people watching us at this moment, but still, maybe any questions at this moment? Then I think we can finish at this point. Thanks for your time. Okay, there is a question from Dmitry Sepp. Hi, Roman. What is the current status of this proposal? Has it been reviewed upstream? It is some part of this proposal is reviewed already, and this actual proposal is based on a lot of review comments, and some part of this proposal still require additional review, and I believe we can make some adjustments after the review. And another questions, and from the Peter, have there been any RFCs to video for Linux and KMS subsystem for the constraints API? As far as I know, constraints API is pushed by three or more community engineers, and there is there was some proposals for KMS, and you can find more by searching for in YouTube for XDC 2020 allocation constraints. There was a lot of proposals in this topic. There is also some sketches in the form of the source code how these constraints can be merged together, and no actual patches on the review at this moment, as far as I know. Any more question? Hi, Roman. About constraints, I'm looking at the four you listed. Yes, I can find any more constraints, but this for at least for IRM platforms. So I know that there are some exotic hardware that require more than this. For example, for splitting Luma and Chroma planes for video buffers to locate them into different banks and other exotic hardware, but like it's an exception, and in a general rule, only this four is does matter. If you know another examples, please share with me. I will appreciate you. So if there are devices that have an unlisted constraints type, I'm not sure I can tell it now, because first we need to summarize all these devices and all this that constraints, and we should elaborate how to deal with them first. So we should prepare the metrics first of these devices and constraints. Anything else? More question? Okay, if you have more question to me, you can always find me on the GloDroid GitHub page. Ask question on the issues tab. I also available in the Discord channel, GloDroid Discord channel. My nick is rsglobal, and you can ask any questions. Contact me if you're interested in the pushing constraints API and generic allocation API. So thank you for joining. Thank you for listening. Have a nice day. Bye-bye.